So I would like to start from very basic of differential equation, and I will only discuss the ordinary differential equation, not discuss the partial differential equation, because there is another part of this lecture is the dynamical system, for which we need the ordinary differential equation. It's generally we use, and today my plan is to give a very introduction to ordinary differential equation, simple, and maybe tomorrow I make things complicated. And so let us start with differential equation. So do you have any idea what is differential equation? I think everyone have the idea. So any mathematical equation which relates its derivative to the variables, then it is called differential equation. So the equation have the derivatives involved. So simple is a very simple equation will be a general one is this one, okay, and it can be higher order, which we will discuss later. So in general this could be a example of differential equation when you have a derivative and variables are there and the derivatives of the variables are there in the equation. So this is the general. Sorry. Oh, sorry. Yeah. I just and so there are many analytical methods to solve this differential equation, and differential equations are very important in physics because we model the natural phenomena using the differential equation. This is a key area of physics where we should know the techniques to solve the differential equation. Now differential equations can be classified into two different classes. So one is ordinary differential equation, and another is partial differential equation. Yes. So ordinary differential means you have no involvement of partial derivative. So what is partial derivative, if you remember, of x, y? So if I want this, so there will be del f by del x into dx plus del f by del y into dy. So here actually if you notice there are two independent variables. So for the ordinary differential equation there is only one independent variable involved. Yes, so simply you can say there is only if f is only function of x, so this is df by dx you are saying. Okay, there is no other independent variable involved. So here is more than one. More than one independent variable involved. So in this lecture series, we will focus on this one mostly. We are not going to discuss the partial differential equation because this is helpful for us to understand the later part of the course, which is dynamical system. And if I want to discuss this one, I will not have enough time. So that's another reason for this. So let us get familiar with some terminologies. So the so order and degree of differential equation. So when I write dE is differential equation. Chandra, it's not dark energy. So order is the highest order derivative involved in the equation. So suppose I have something d2y by dx2 plus dy by dx equal to some f of x. So here I have the order of differentiation, highest order is 2. So order of this equation is 2. Now if I have to go for degree is the power of the highest order derivative. Okay. This is a very basic thing, probably every one of you know. So suppose I have how shall I write? Some differential equation which is like this. So this is something, I don't know even the solution exists for this, but let us consider for example. So what is the power of this differential equation? What? 2 or 3? Order? Yes. So because you should not count this one, this is not the highest derivative involved. The highest derivative is this. So the order will be degree will be 2 and order is also 2. Okay. So this is very simple thing. Now just to get know to some terminologies. Now let us discuss about linear differential equation. A differential equation could be linear and non-linear. Okay. So how do you know differential equation is linear or non-linear? Do you have any idea? Yes.
Linear combination of the solution is the solution.
Yeah, that is means when you know it is linear, then you impose that. I think that also a check, but there is more general form. So D differential equation, which is which is linear, have power of the dependent variable and derivative to be 1 and there is no multiplication. So I can give you a more general form. So suppose you have a differential equation which is like this. This should be ax and dy by dn plus a0y equal to sum gx. So that if this is a very general form of your differential equation, okay. So the check is that so the first check is that all derivatives has to be the power of 1. And there is another is that all anx and gx is either constant or a function of independent variable. Do you understand? So this is, you have to check if there is a square or cube of the derivative, then it is gone. It's a non-linear system. But even that is not there, the next check is you have to check all these coefficient and this one right side, right hand, is either function of the independent variable, means either function of x or it is a constant. So let me give you some examples.
Sorry.
Yeah.
And this one,
an x.
X, not
Yeah.
N.
No, not n, sorry. My n and is degenerate.
I get used to it.
Yes. Yes. Generally, when I write in pen and paper, it's not that degenerate, but on board it becomes. Okay, so tell me what is this equation? Is linear or non-linear? Yeah. That, So is this a linear or non-linear equation? Really? See all the coefficient, they are constant. And see that gx, this is gx, function of dependent variable. So even it looks very weird equation, this is a linear equation. And the superposition of the solutions will hold for this one. And something very similar like this. And what about this? this is a constant, this is a function of dependent variable, but independent variable, but this is a dependent variable. So this becomes a nonlinear.
Sine y.
Yeah. This is a
Look like delta function.
okay. So this is yeah. This is non-linear. So this is the general definition to understand if a differential equation is linear and non-linear. If you have any question here.
Confused about the first equation. Because I think that second of this x to the power 4.
Oh yeah, sorry. Yeah, yes. But x is a dependent, independent variable.
Yes, but you say that linear is power must be 1.
No, power of the derivative I am saying. What I wrote. Derivative. Oh, this might be wrong. Yeah, but this only derivative. Yes, derivative. And you have to check the other coefficient and this one. Is it okay? Any other question? Where is my note? Let me check my note.
The last term of the first equation is gy.
Mm-hmm.
The first equation.
First equation is gx.
The last term of the
5x. 5x. Anything you can put. It's a function of x. gy. Yes. G is a constant, some constant. Yes.
Is a function of x?
No, I just put some constant actually. I don't write it as a function of.
Even if it's a function of x.
Yes, function of x will make it linear. Maybe this was I should. No, this is correct now. The which is linear and don't have the power is 1 for the dependent variable. Oh, this is correct. I wrote correctly. Yeah. So this is, you see, this is 1 dependent variable. So y should not go more than 1. Yeah. Yeah. This is correct. Yeah. Because I write not independent. It's a dependent. Y. Yes. Yes. So yeah, it should be correct. Of that. Yes, and you have to see that there is no higher power for dependent variable and the derivative.
Yes.
And if that satisfies, then you go for the next one.
Okay.
So then, actually, if you have something sine y, you see there is higher power. You can open it up for the series, and there will be all higher power. So it's become a nonlinear differential equation. So now a differential equation could have different types of solutions. So any question? Which one shall I? Middle, like, okay. So there could be type of solutions for differential equation. So the first one is the general solution.
The top of the case, the type solution of different
Yeah. Maybe it will be types.
types.
Types, no? More than one, yes. Yes. So these are the most general solution. With so the general solution is the one which is the, that's why it's general, because it's a general solution and it will have the number of arbitrary constant in the solution to be equal to the order order of the differential equation. You understand? So suppose you have something d2y by dx2 is maybe x, okay. So I can simply, so the first solution will be dx dy by dx equal to x. So dy by dx will be x square by 2, yes, plus one constant will come. So next will be y will be, this will be 3. So this is 1 by 6 x cube plus c1x plus c2, yes. So this is the simple form, the general equation of this differential equation. And as you can see, how do you know this is the general solution? The number of arbitrary constant, which is C1 and C2, is equal to 2. So that's a check. Now the second thing, second is particular solution. Particular solution is obtained from the general solution when at least one arbitrary constant is supplied. So this general solution will become a particular solution when I have some situation and I know the sum of the constant. I suppose I make this C1 to be 0. So then the solution, this one, will be a particular solution of this one with some boundary conditions. Is it okay for you? So this is very, very basic thing. So you know, so, and there could be another class of solution which is called singular solution. And the singular solution is that one which is singular, means which cannot be obtained from the general solution. So you that is kind of a completely different class of solution which has no link with the general solution. So that is a singular solution. Okay. Is there any question? Is it okay?
This is unlike what I learned from my undergraduate.
Yeah.
I never learned singular solution. It's the second one.
Yeah, singular solutions. I don't have any particular example in mind,
Yeah.
but there could be some solution which.
And so they told me that it's order to that is to arbitrarily constant.
Yes.
for one.
Yes.
Yeah.
So suppose I can give you very easy. Maybe if I have something in mind. So suppose a differential equation which you can get by x square plus alpha square. Okay, so this will be 10, no? 10 or 10, I think. So this will be 10. Now, 10 x by alpha something, I think, as far as I remember. 10 x by alpha. So this is a parameter. Okay. But if I same class of solution, if I put alpha equal to 0, so that's a singular solution of the same thing, because alpha is the arbitrary constant. But you cannot deduce from 10 to, so suppose alpha is 0 is x to the power minus 2 dx. So this is going to be minus 1 by x. So this is like 2. There is actually that mapping does not exist for the integration is different for these two.
Can you give us an example?
Of the singular solution?
Yeah.
So yeah, that's what I'm saying. Like suppose you have some differential equation which can be obtained by this. So suppose this is dy, and when you solve it, this is dy equal to tan of this plus some k. And now I make alpha is my arbitrary constant. I can make alpha to be 0. But if you make alpha to be 0, and if you try to see from the differential equation, it's a different solution is minus 1 by x, which you cannot get by adjusting. Sorry.
So log is a singular solution.
Yeah, this is a singular solution. So there is no connection between this and this.
Okay.
Yeah.
But then maybe the student will be lost already. Right?
Already lost?
Yeah. Can you just solve it?
Yeah.
Just try to
Do it again.
Yeah.
This side.
Show
Okay. Formally. Okay.
Yeah, more formal.
Okay. So suppose I.
I know what you mean, but then I think the student is
Yes. I understand. So suppose I have this equation. So this is one equation I have, differential equation. Now this alpha is arbitrary. Arbitrary means it can take any value from minus infinity to plus infinity. So if I solve it with a arbitrary alpha, so what will happen, dy will be dx by x square plus alpha square. So now if I do dy is dx by x square plus alpha square, this is this y is going to be 10. There will be 1 by alpha, no? 1 by alpha here, yes, 1 by alpha. Arc 10, yes. So this, sorry. arctan x by alpha plus some constant C1. Okay. But suppose I have another choice of this same differential equation, I make this alpha to be 0. Yes. So, alpha, if I make alpha to be 0, so what will be this? Tan infinity inverse infinity is, let us do it from here, tan cos theta. So, tan inverse sin theta by, so this is infinity means cos is 0. So, theta is pi by 2. So, you will get something 1 by alpha pi by 2 plus C1. But if I make alpha equal to 0 from here, see this differential equation, start from this differential equation, it will have x square dy equal to dx. So, dy is 1 by x square into dx, and you will get y equal to minus 1 by x plus some c. Yes. So, this is same class of same class, but this cannot be obtained by any from here, means the mapping in more mathematical term is not there. Okay. Any question? Any other question? So, another important thing for the differential equation, particularly for us physicists, is the boundary condition. So, boundary condition is so when we represent a physical process by differential equation, it might be two boundary condition. So, boundary condition is B and C to yeah. So, when we express a physical system or through some differential equation, then that differential equation might be subjected to some boundary condition. So, what should I give the example? M d2x so this is the harmonic oscillator, no? So, for this harmonic oscillator you could have different boundary condition to solve when you are after solving this, how you are releasing this. Okay, so if this is your boundary the pendulum, so you can release it from here where x will be your A and V is 0, so you just release it from here. So, why boundary condition is important in physics? Because mathematically you can have a landscape of solutions, means there could be a huge number of solutions exist for a differential equation. So, now when we explain the physical process using that differential equation, we have to find out the solutions which are more physical, and that is why the boundary conditions are imposed. And boundary conditions can be many different types, so which I am not going to explain here. So, I will now next jump to the solving this differential equation. This is the kind of terminologies for the differential equation. You have any question? Yes.
This boundary condition is the same as the initial condition.
Yes, sometimes, yes. They have this kind of Dirichlet boundary condition and many, depending on when you give. You can give it at the initial, you can give it at the final. So it is the same.
So for each hour we should have 5 minutes break for each.
Yeah. So we started at, I think, 51. You want a break now? We are already 15 minutes late. Started. Okay, maybe 5 minutes break. From the choice of arbitrary constant, you cannot come to this one as a solution. So this is a unique solution from the general solution. It cannot be deducted from the general solution. That's why they call it a singular solution. Mm-hmm.
You have to set, if you want to y is 0,
Mm-hmm.
which means that only one way that you can have satisfy this answer.
Yeah. This one. So
Only
x, the whole x-axis. Yeah. X minus c. This is a particular point where it is going to cross. You know that one.
Yeah, but which means that you have to set the value of x is minus c only, which make this.
But x is a variable.
Yeah, I mean.
When you make, suppose you choose a c to be something like 1. So this will touch the y-axis at x equal to minus 1. But that is not the solution. That is touching it. But this is the y equal to 0 means whatever x is you have, a whole x-axis is your solution. In phase space, you will see this. There is a like trajectory lying on the x-axis. But that is a singular solution for this. So now this is all about the kind of definition, very basic definitions of when you try to handle differential equation. We will jump into solving the differential equations. Okay. Yes, please.
You should give a definition for y prime as well. Otherwise,
Y prime is
y prime.
okay.
Yeah.
Sorry. So this is like we'll see how to solve these equations and let's start with the first order differential equation. Now first order can have both degree 1 and higher degree. Okay, it can have. So first order means I say that means there will be only dy by dx. Yes, that's the part, not d2y by dx2 or higher, but it could have something like dy by dx and dy by dx to the power n. Okay, this is my n, and this is first degree, and this is higher. No, this is order, and yes, this is degree. Okay, so we'll be first studying the first degree, first order, some methods for solving first order, first degree.
And that's sorry, I'm too comfortable.
Yes, no problem.
Relax.
So can I rub this part?
Yeah.
So the most simple form of first order first degree. So there is no square of dy square. The one I showed it here is actually first order second degree equation. So how can I solve? We solve this one. So the first method is called what shall I call it? Separate the variables. So suppose you have a differential equation and for the differential equation the solving it is for linear system is there are methods you can solve it, but which method to apply you have to see and inspect each differential equation case by case. Okay. So it's not like everyone is going to be solved by using a single method, case by case, and there could be something which you cannot solve even. That is also possible. And for the nonlinear system, when we will discuss it tomorrow, it's more complicated. So you might not find any analytical solution. So you have to go for the numerics to find the solutions in those cases. So this is the most one of the simplest case. So where, sorry, I make a mistake. This would be y. So this is called separate the variables. So separate the variables means put the x in one side and put the y in another side. So dx. So as you can see, this you can do very easily, and then you can just do the integration and you will find the solution for y as a function of some function, maybe g is there, so maybe some function w of x. So this will be your solution for this using this method. So a simple example would be, all of us know this thing. So suppose I put yes, so this could be done very easily, and you can do y square dy equal to x cube dx, and then you integrate it and you know the solution of this one. Okay, I am not going to integrate it. So and another more a little bit complicated example I could give you, and or maybe you can try to do it now. It is very easy. D yes, so this is example 2. So this is also this can be done very easily. Have I do? This should be square. Then only you can integrate. And this method has some very application to some very basic physics, like one is like if you like know from physics is the radioactive decay. You know the radioactive substances, they decay, and the decay rate is proportional to n. N is the number of atoms of the substance. So, you can make a differential equation out of this argument is that the change in the number, total number of the substance is proportional to the suppose lambda n, and since you see it is a decay, it is not a growth. So, the decay means there will be a minus term here. Okay, so, this is how we do simply model the physical system. So, if you solve this one, lambda into t, and so this is ln n, sorry, yeah. This would be dt, no, I guess, lambda t plus some constant k, and so you have n equal to so this is, I can write L equal to ln n0 because this is arbitrary constant, n equal to n0 e to the power minus lambda t. So, this gives you the decay of a radioactive substance if you know the decay rate lambda. So, this is a very simple example of using first order differential equation to study the physical phenomena. This could be more complicated. I will show another example later, that if you have a, they call it mother and daughter, one substance is going to the another substance. So, you will have a bit more complicated system, but you can solve it there. Okay. Any question from anyone? Very simple. Yes. So, now is homogeneous differential equation. Do anyone have any idea what is homogeneous differential equation?
N is equal to
N?
from the definition.
Yeah. Yes.
The function that
Mhm.
multiplied by the derivative
Mhm.
is a constant.
Yes, but
And
yeah.
gx
Mhm.
on the right hand side is 0.
Right hand side go to but that might not be necessary. Right hand side might have something, but there is a like more physical term is that scaling property holds. So, first if you want to know homogeneous function, I will give you a very simple definition. So, homogeneous function is something which is f of mx and m, again my m and x, my is something suppose m to the power n f of x y. So, this kind of functions are called homogeneous functions. So, if you scale the variables, so you get a multiplicative factor and you get the original function back. So, then this n is called order of the homogeneity. I am not sure if I write it correct. So, suppose I can give you an example of it is x cube plus y cube. So now if I have something mx and my, so this is going to be m cube f of xy. Yes, you understand? Put mx for everyone. So this is a homogeneous function of order 3. Because this m, the constant factor come out with a power of 3. So the order of the homogeneity is 3. So when you have a differential equation, which we already write, is f of x and y. So at that time, if this f of xy is a function of two homogeneous, ratio of the two homogeneous equations, you can say, a homogeneous function. I will show some example. Then this is a homogeneous equation, differential equation. So then what I can write here is that it is always possible for you to write both of them. So if I take x cube outside from this, so you will get x cube y by x. So it's a function of y by x. You understand? So suppose I write it x cube function of y by x. Do you agree with me? This one. So the x will come out as the so in that way we can write it like this one, x to the power n phi y by x and x to the power n, this should be maybe psi y by x. So we can write this side as some function eta y by x. So why I am discussing this is very arbitrary way, but yes.
From this we mean that m can be anything out of the constant.
M, yes, means because of that property you can take this one. Yeah. Because if you again now if you have a this to be 4, you see there will be m here. You cannot get back the original function. So homogeneity will be lost for the function. So that's why you can take x out and you can write it f of y by x. Otherwise the homogeneity got lost. Means there are many different way of mathematically defining it. So but this is simple, I try to do it with the example. But if you go to mathematics books, this complicated theorems they have. So in this kind of situation, the method for solving is called what do you call? It's a yeah.
Can I
Yeah.
ask you to
Yes.
repeat again when you say x cube f of y over x?
So this one you are saying? So this is my f of xy is x cube plus y cube, and now I take x cube outside. So if I take x cube outside, so this will be y by x whole cube. So this is like I write x cube is a function of y by x, some function of y by x. So this property only hold if this function is homogeneous. Suppose this I make 4. So this then I cannot reduce it to y by x form. So if I write it x cube plus y to the power 4.
You were saying that this example
Yes.
is a homogeneous,
Yes, homogeneous.
but then it's m, it's not x. So we say
Even if you have the means the m the
That
The taking this m outside is ensuring that these powers are same
Yes.
from the definition actually.
So when you say x to the third cube, y by x, okay.
Yeah.
But then m seems to be a constant and x seems to be
Yeah, variable. But what I'm saying, this is the definition, but this is kind of a property. This is the definition of homogeneous function. So suppose if I could do this one, that means the power of these functions are same. The total, there is no like 4. So if I have this one 4, can I get back the original function? Cannot get back the definition.
So my point is that you want to define m as a constant of
Yes.
parameters.
Yes, yes.
So then y and yx is to the cube.
Yes.
I mean.
Okay, can I do it again? Yeah, let me see. So means this is the definition I am saying for the homogeneous function is f of x y is some m to the power maybe n f of mx my. So when I put mx my, so m to the power n f of x and y. So what I did here, I replace x by mx and I replace y by my. So it's like physically you scale the system. But what you get, the whole quantity is just multiplied by some constant. And then if this is true, then the next, this one ends your, when can you get this one? So this one only you can get if you have something like you see the power, 2. And this definition ensure that all the variables have the same power. Not same power, means the total power of the all variables are same. Now if I have this one, now let me take x square out of this. So I get 1 plus y by x plus y by x whole square this. So then I can write, then only I can write this is a function of y by x. So this is the definition which ensure that this hold. And from that property is this is the kind of a, you can derive this property of this kind of functions.
That's mean if we have the function satisfy the condition, we will.
Yeah, you will get this one definitely. So this is the property of the function. Is it okay? To check if it is homogeneous, you can check with this. If it is homogeneous, you will find out this one. I think we can say in cosmological terms, scale invariant, something like scaling is.
But then I have to check.
Okay. Yeah, you can check.
Should be correct. Should be correct. But then the thing we didn't show it implicitly how to transform x to the mx and y to the my. So it's just going on.
Yes. So any physical example can I think of it? Anything which can scale.
What confused me when you say when you write down x, small x and capital X.
Oh, sorry.
So,
Okay. Let me put it like this way.
yeah, even worse.
Okay.
Okay.
I'm trying to, like, as you say, my x is So in place.
Now you have to use Times New Roman.
Yes, so I used to change my font so that it maybe in few iteration I will be not making mistake mixing font. And yeah, so the technique for this is, if you have a differential equation like this, where you can write dy by dx is sum g of y by x. So the next step is you have to consider u or v. Generally they consider it y is vx. You know it, no? This technique work for the homogeneous differential equation. So once you do it, then you have to find, next step is you have to find dy by dx. What is dy by dx? So this is the first step. Second step, third step is solve for v, and fourth step is substitute y. Yeah, substitute v equal to yes, v equal to y by x. That's correct. Then you get the solution. So this is, but this only work for homogeneous equation. So let me give an example to you. Yes, it's Times Roman now. Okay. So if you see this one, yes, so is it a homogeneous one?
Yes.
Yes. So homogeneous one means you can take x square outside from that, and the whole things will be becoming, yes. So if you take x square, so this will be x function of y by x. So then means you can use the y equal to vx form method. So you put y equal to vx, so dy by dx is v only. Yes. So now you have to replace everything here. So you get v plus x dv by dx equal to, so now we need to replace, so what we have is, if I consider x outside, so this x will be here, so I have 1 plus v square and 2v. Is it correct? Yes. So now you got some equations which is in terms of, so you can take this, it will be why I have a x, is it correct? No, oh wait. Oh, to write it y by x, I consider x square out, no? So there will be no x here because I took x square out. So this will be y by x. Is it okay? Oh. Yes. So I just took x square from both sides. So then I have to put 1 plus v square by 2v minus v. So this is going to be 1 minus v square by 2v. Yes, that's correct. And then you can solve this equation. It is a solvable Now it is you use the first method, which is the separate the variables, that method. So in that case you will get 2v by 1 minus v square dv equal to dx by x. Yes, so this will be minus ln 1 minus v square equal to ln x plus ln c. So then you got x 1 minus v square, yes, 1 minus v square equal to c. So again 1 minus v is y by s, y square by x square equal to c. So what you get is x square minus y square equal to cx. So this is the general solution. Is it okay? So to apply this method, the first check is the check for the homogeneity of the differential equation. If it is homogeneous, you can apply this method. It's straightforward. Now can we deal with some very simple non-homogeneous method differential equation? Actually we can handle using this method very simple non-homogeneous you can reduce to it to be homogeneous. So I just give one example. I will not solve it. Suppose z. So is this a homogeneous differential equation? Is this homogeneous? Look at it. X is power 1, y is power 1. There is no variable here. So there is a mismatch with the power. So if you put x equal to mx, y equal to my, but you cannot get back the m to the power something equation. So it's not a homogeneous differential equation. So you cannot directly apply this method. But what you could do, you can reduce for this case only. You can reduce it to the.
Can you change the D constant to another?
Oh, okay. Oh, I mixed the font again. Okay, y. It's okay. Y is okay. So what you can do, you can have a transformation where you have this capital X is, now I have to go back to what kind of font? Maybe this is my small x, okay, by h. And if I have y equal to sparse maybe k.
You can use this original font, it's okay.
Because people are mixing. So
Original font is okay. Yeah, you should.
yes. Then dy by dx is going to be, what do you see? I put it will going to be a. Sorry, I make a. This should be a wrong opposite. I think I should make this one small x. It is same, but to be consistent with my notation. And small y is capital Y plus k. Okay. So as you can see, dy small y by dx is the same d capital Y by dx. Okay, there is no change because these two are constant. So now I put x for this x, so a capital X plus b capital Y plus a h plus b k plus c, and this will be f capital X plus e capital Y plus this will be f h plus e k plus g. Okay, so remember this h and k is my choice. You can choose it. So now you can choose it such that these two, the extra part, this one and these two extra part become 0. You have the right to make it 0 without any problem. So you can write ah plus bk plus c equal to 0, fh plus ek plus g equal to 0. So when you have that, you can find the solution for h and k. So now if you make this 0, this is a homogeneous equation of capital X and Y. Then you go to that method, apply it. So I just give you one very small example to reduce it, but I don't go for the solution, so that student can have a concrete idea of this. So suppose dy by dx is x plus y plus 3, and this is x minus y plus 3. So this is not homogeneous, this is non-homogeneous. Yes. So then I took the same, x is capital X plus h, y is capital Y plus k, and if you put it back, dy by dx is going to be x plus y plus h plus k plus 3. You will have the similar x minus y plus h plus k plus h minus k plus 3. So now you have two equations, h minus k plus 3 equal to 0, and you got the solution for this is k equal to 1 and h equal to 4 if you just solve it. So, but once you choose these to be 0, you are left with this differential equation, which is x plus y and x minus y. So homogeneous. Take y equal to vx, solve it, but remember, come back to the original one. Yes. What is the transformation? After solving this, the transformation is x plus 4, and this is k, no? Y plus k, y plus 1. Put it here, you will get back this one. But once you solve it, you have to come back to the small x and y. So that's the thing. Any question? You have any question for this? Any question? Oh, it's too easy, I think. This one? No, this is caps. Because I change in the coordinate. I change. So small dx by small dy, what we will get? The same, no? Because this is constant. So d capital X, d capital Y. It's the same thing. Because those are the constant. Okay? What? right?
Okay. Okay. Now I a little bit confused because I substitute small xy in the first equation.
Small xy is capital X plus h, capital Y plus k.
And then I will write
Small.
small in the right.
Yeah, but okay, you mix it then. Then you have to make it two coordinates to be different. So this is another small example that you can even handle some non-homogeneous differential equation with this v equal to yx structure method, but it's very limited. Only you have this form, not other forms are not doable. So next is what I want to discuss is exact differential equation. So this is a particular type of differential equation. Let us see. It is very important that you have hold on this kind of differential equation because they are the structure of all of science and engineering. So suppose this is in the form p x y and q x y. Okay. So you can have something which looks like q x y dy plus p x y dx equal to 0. Yes, if I have it without any problem I can do it. But now let us try to see that I have another function u x and y. So you have a differential equation of this form, then you consider a function u x y, any arbitrary function. So I take total derivative of x y. So what you have, del u by del x, yes, into dx plus del u by del y into dy. Yes. So but look, these two are in the same form, except you have to make it to be 0. Then this du could be the u function of xy is constant. If you can get some function like this, is going to be a solution of this differential equation.
Isn't Q?
This is q and this is p.
Okay, I thought it's 2 and circle.
Oh.
I number 2. Sorry. What do you mean?
But when I write in iPad, AI can understand. AI is more now intelligent than human. So this is 0, that means this d u x y equal to 0. So u x y is a constant, and that is actually solution of this differential equation, if you can find. Yes. So this is called exact. So if you got a differential equation like this, that is called exact differential equation. But first, like the homogeneity, you have to check for a differential equation of this form if it is a exact differential equation or not. So if you, when I compare this one and this one, 1 and 2, so what is my q? Q will be del u by del x and p is del u by del y. Yes, just I am comparing these two. Am I doing anything wrong? Yes?
Del u by del x is equal to p.
Del u by,
Yes. But
oh yeah, del u by del x is p, yeah, according to my notation, and this will be q, no? Yes.
You will have coffee.
You want coffee? Yes. And then the check for this differential differential equation is exact or not is del p by del x, del p by del y, sorry. Yeah, I need a copy, I think. Yeah, del p by del y, which is going to be del 2u by del x, del y del x equal to del 2u del x del y, which is equivalent to del q by del x. So this is the check for the differential equation to be exact. Let me have some water. Not exact.
Exactly not exact. Exactly exact.
So if you have something like this, if you have something like this, then we try to solve in the following way. Let's do it. I give one example, 4x cubed plus 6x y square is dx by dy equal to minus 3x square plus 2xy plus 2. Okay, so if you have this one, so as I tell you, do this way. Yes, so you got your P and Q. So this guy is your, maybe I did a wrong thing. The 3 will be here, I think. The 3. Okay, so this is Q and this is your P. And now we have to check first if you got del P by del Y. So what is del P by del Y? Del P by del Y is 6x plus 2y, and del Q by del X is 6x plus 2y. Okay, then exact.
Have you ever heard this notation as curl P by curl Y?
Curl P.
Is India say that? Or
This one?
Del?
Del, yes.
Okay.
What is
In Thailand, we call curl P by curl Y.
curl? Oh, curl is this for us.
Yeah. I just realized that this is what the Thai education is wrong, because when they went to abroad,
Yeah.
they say curl P by curl Y. Or one.
Yeah. Curl means there is a direction and it's complicated.
Everyone who holds a curl in this country
Yeah.
realizes it's wrong.
Yes.
I thought, curl
Yes, yeah.
เพราะว่า
You can create del or partial.
yeah
Eh,
in UK they call partial
Yes,
จะเป็นโคด
yeah.
โคดประเทศเลย
Carl is this is a vector.
กรุงเทพเลยผ่านขึ้นใหม่โคดหมดเลย code all the universities say code everyone in the world say code
Yes. So how we go next? Next will be very easy. Yeah, find the function u. How do you find it? So the p is your del u by del x. So just take p or q, anyone. So del u by del x is your p, and you know what is your p. P is 4x cube plus 6xy plus y square. So what will be your u? You have to integrate it. So the integrate the whole thing will give you x to the power 4. I'm just doing, this will be x to the power 4 plus 3x square y plus y square x. But remember, this is a partial. You are integrating on the partial derivative. So you should not let it free of some y. It could be function of some y, some function of y can be there. So if you take derivative with respect to x, so you will get this one. So there could be this one. So now what is your q is del u by del y. So then you have to make a derivative with respect to y of this one. So you claim you got a u. So what is this? 4x cube plus no, it's a y, no, 3x square plus 2xy del phi y by del y. So you are saying this is your q, but in the differential equation you have been given in q. So now it is mandatory that you check this q, both the definition of q valid. They satisfy. So you got this one cut out, this gone. So del phi y by del y is just your 2. So phi y is 2y plus some constant c. So then you have to put here, yes, 2y plus c. So you got the solution for this differential equation. Is it okay? It's very easy. So each case by case you have to check which one you want to use, which method you want to use. And I have to stop by one more method. I finish then. The next method is, because I already started 20 minutes late. Yeah, the next one I am going to discuss is one of the very important in for the differential equation, solving differential equation, is the particular integral. Probably you already know the how to do with particular integral. So let us consider this is the very general form of a differential equation, which is py equal to qx. So I go very fast so that we can finish on time. So suppose this is a differential equation. This is one of the very common differential equation we physicists encounter.
P is the function of x.
No, this could be,
Constant.
yeah. This could be function of x also, I think. Yeah, this could be function of x.
So now your x look very similar to n. It's qn.
Okay. So
X, yes.
then suppose I got, so if qx could be 0 or non-zero, okay, but I took it as qx equal to non-zero. So then I can have a arbitrary function which looks like ix, and I multiply ix to this equation both sides. If I do this, then I can demand that this left hand side is equal to a total derivative, which is ix into y. Okay. This is just, I am imposing that the left hand side is, I multiply both sides by ix, then I say this left hand side is equivalent to this total derivative of ix. Now I can do it dix by dex into y plus ix into dy by dx. So what will happen that one term should cancel now. Which one cancel? This one and this one cancel. So what you left with is p ix into y is actually am I doing wrong, something wrong? Just give me a moment. Y ddx ix p y, oh yes, this one is equivalent to this one, yes, d ix by dx into y. So the ix is going to be e to the power px or dx. The p can be x function of x also. Okay, so why I want this one to be total derivative, left hand side is total derivative, means I can take a total derivative and multiply dx this side. So this could help me to solve the equation of this form. And once I have it, I can write dx is ix into y equal to q into ix. Okay, so now you don't have to think about, you get d and then multiply dx there, and then you have to integrate it. So this is the, and I give you a very quick example for this one, and then we can stop for the today. So here my p is cos x. P is cos x. So my integrating factor ix is going to be e to the power cos x dx. So this is e to the power sin x. So just multiply e to the power sin x to both sides, you will see the left hand side becomes a total derivative. That's the good thing about this method. E to the power sine x dy by dx plus y e to the power sine x cos x equal to half sine x e to the power sine x. So, this is dx of y e to the power sine x. Can you see it? This is the total derivative of this side, and this is going to be the same half probably this should be 2x. I make a mistake for the otherwise the integration will be difficult. This is going to be 2x sine 2x. So, sine 2x e to x. So, this is not a difficult thing to integrate now. So, the left hand side is y e to the power sine x equal to integration of, so sine 2x is 2 sine x cos x. So, cos x sine x and then e to the power sine x and dx plus some constant because we already performed this integration. So, y e to the power sine x equal to, now what we can do is we can consider sine x equal to z, some other variable. So, if you consider, then it will be z e to the power z dz plus c and y e to the power sine x, and you have to do it by parts. These are very simple integrations, so I am not doing it. It's like I leave it to you. Because I make a mistake. The definition.
Okay, so that means you have to change.
Oh yeah, this is only x. Sorry. This is only x. Only this 2 is changing. Sorry. And then what you will get, e to the power z into z minus 1 plus c. So, the solution will be y is sine x minus 1 and plus c into e to the power minus sine x. So, as you can see on first order differential equation, so there is only one constant involved. So, this is all about, there are a couple of other methods like Bernoulli's form for solving differential equation, which is also very similar to the like finding integrating factor, but I will not have time to do these things. Tomorrow I plan to do some second order differential equation solving technique. Only 2 techniques I will discuss, 2 or 3 very quickly, then I will move to dynamical system. Any question you have? Oh, I did it. I did it on time. Yeah. Thank you.
Okay, let's thank Nandan.
Yeah. So, yesterday we restrict ourselves only to the first order differential equation. Today we spend like I plan to spend half an hour on higher order differential equation. I will go a bit faster than yesterday so that I can finish it. So, the higher order differential equation is something I write the polynomial higher order differential equation yesterday. That is the general one, but the one we are most interested in physics is the second order differential equation. It has lots of application in physics, and particularly our equation of motion is second order differential equation. That is why it is very important for us. So, we will go very quickly about some techniques of solving second order differential equation, then I will jump into dynamical system. So, this is called a second order linear, this is a linear equation, homogeneous linear equation. Okay. So, now if you see this one, so since it is a linear equation, what Chandra was saying yesterday, so the superposition principle for linear differential equation hold. So, if you got two solutions y1 and y2 are two solutions, then y is c1 y1 and c2 y2. So, this y is also a solution. And what is the necessary condition for this y1 and y2? They have to be they are not only two solutions, they are two independent solutions. The another criteria is they are independent. They are two independent solutions. So, how do you check they are independent? If you have y1 and y2 and y1 prime and y2 prime with respect to x is not 0. Okay. So, if this determinant, this is called Wronskian, if this is not 0, then these two solutions are independent solution of this differential equation. So, for example, let us try to solve this equation in a general way. So, one of the most used technique for this one is, let consider a solution y equal to e to the power m and x. Okay, m and x. Yes.
This kind of a Wronskian again.
Which one?
Wronskian.
Oh, let me write. I think this, I am not sure if I.
Please describe it again. I missed.
Oh, that. So maybe I show you here the example, so you will understand better. So, if you consider y to e to the power mx to be solution of this equation, so you can put it back. So, you know dy by dx is m e to the power mx and d2y by dx2 will be m square e to the power mx. Okay. So, if you substitute this one to this equation, you will get m square plus a m plus b 0. Yes? Any?
Similar to the
The x. N is this, no? My x is this. Similar? Okay. Yes. Yes, okay. So, this could not be 0 because you already considered it to be a non-trivial solution. So, if it is 0, then it don't make any sense. So you have to solve this one m square plus am plus b, and you know how to solve it. Yes. This solution of this was given by an Indian guy. His name is Sridhar Acharya. So the solution of this is m is minus b plus minus square root of b square minus 4a and no, not b square. Did I make? Okay, this will be minus b is a and a square minus 4b into 2a. So depending on the behavior of this, so you see you have two roots. One you can call the m plus and m minus. Plus corresponds to plus, minus corresponds to minus. Yes, Donna? Two. Yes, because a in my mind I have the notion a, b and c. So I have followed. Sorry. So m plus or m minus, or you can consider sometimes m1, m2, whatever you want. So the solution, the one solution is y1 is c1 e to the power m, maybe better I put m1 and m2 is and y2 is c2 e to the power m2x. Now this is the check if these two are independent. This is the Onskian you have to consider. So y1 and y2, correct, and y1 prime. So this is m1 y1 and this is m2 y2. Yes, and if you see the determinant, this is not 0. So they are either m1 equal to m2, it is not 0. So they are two independent solutions. So you can write the complete solution for this is c1 e to the power m1x plus c2 e to the power m2x. This is the most general solution. But this solution can be classified depending on the behavior of this thing. What do you call this one? Under the square root we call, there is a particular name. Sorry? What? No, this side, this thing inside this, there is a particular name of this. I forgot mathematical name of this. I forgot of this. So shall I rub this part? So what is your m1? M1 is half minus a plus square root of a square minus 4 b, and m2 is the same plus okay. So if this is now depending on this behavior of this, you could get I think three to four classes of solutions, 3 or 4, 3 classes I think. So the first one is that a square is greater than 4b. So this term inside is actually is positive. Yes. So that means you have two distinct root, m1 and m2 are two distinct root. So you will just follow that one. So you will have c1 e to the power m1x plus c2 e to the power m2x. This is the first case. The second case is when s square equal to 4b. So a square equal to 4b, that means m1 equal to m2. Yes. Yes, m1 equal to m2. So now this is the interesting case. What is the solution for this? General solution I am asking. What will be the general solution if you use this one? It's something C1 e to the power mx plus C2 e to the power mx. Yes? X. So then it looks like you got a big C e to the power m a. Yes? But is this a general solution? No, because you have to understand, if it has to be general solution, the order of the differential equation has to match with the order of unknown arbitrary constant. So here the arbitrary constant can be reduced to 1. They are not two independent arbitrary constant. So this is why this is not the general solution. We have to check a bit to find the general solution. Is there any question? No? Rub this one. So then how do we get the general solution for this one? Yes.
Is that the general expression then?
Yes, this is the general expression.
So that is a general solution.
Yeah, this is the general.
But then when you assume this is not a general solution.
Yeah, when m1 become m2, then you can take this e outside, then you have c1 plus c2.
Okay, so you say that the second case is not general solution.
Yeah, this second case. If we follow straightforward this one, this is not going to be a general solution.
But that is a general
There is a solution when other conditions are met.
confusing.
It's confusing.
When you say not general solution, that leads me to understand that this is a particular, but this is a big.
Yeah, this is a particular solution. This is a particular solution. So what I am saying, if you follow this directly to here, it's a particular solution. A very similar example will arise. So I just try to give, suppose you have a matrix and the matrix has the eigenvalue something like this. So what is the eigenvector? You know the one eigenvector immediately, but it's a two-dimensional matrix. So is the there is one eigenvector, there is another different eigenvector that you have to calculate by making it square. So this is like the same thing. When it become degenerate roots, the mathematics is different. It's not the same from the distinct root. I will show this if I get time, that when roots become multiple, then this has to be done in a different way. Okay, so how can we find the solution for this? Suppose there is one solution I have is m1 and another is m1 plus h, and I will take the limit h tends to 0 and make them same. So then what is my y is c1 e to the power m1x plus c2 e to the power m1 plus h into x, and then what can I do? I can take m1 out, so e to the power h x into e to the power m1 x. So now I can expand it with series expansion c1 plus c2 into 1 plus hx plus h x square by factorial 2 yes. So then the argument here is that you have C2Hx plus H into all the higher order term here, and you have e to the power m1x. So the argument is, now you take the limit of this equation and you have this C2 as your arbitrary constant. So make C2 to be arbitrarily large so that C2 and H is finite, it's not 0. Yes? So it becomes a new solution, C plus dx equal to e to the power m1x, and if you check, this is the general solution for the equation.
So C is nx or
Which one?
the third line, hx, right?
H, yes. H.
H.
Yes, this is H.
For the complete solution,
Yes. Now you see you have a two different the arbitrary constant. So this is the general solution, and even you can check it with the putting it back to the equation. And so far so good. Let's
can we check with these two solutions with the Wong scheme? C e power mx and dx e power mx by Wong scheme.
oh, this one and this one you want to check. So this won't be a I think, because if you take derivative you will only get m1 out, so that will be, I think it will be 0 because they are not independent. This is a special solution, particular solution of this when you put d equal to 0. So this is a particular, that's not an independent solution from this one. That is a subclass of this particular choice of this general solution. Yes. Fourth line from here.
Maybe H. Maybe H squared.
Yes. Oh, yeah. That's true. Yeah, that's true.
And they have C2.
C2Hx. Maybe the square will be here. Yes. Yes. This is
And multiply C2.
square multiply. Yeah. Means I took everything inside just to so that the power of h square, higher order of the h. That's, yeah. Thank you for pointing it out. I'm trying to move a bit faster. That's, yeah, because there will be one h, means you only consider up to the linear order and you make the C2 to be very high because C2 is your choice. So then you can make it a new constant which is finite, even you take h tends to 0.
What about H squared? H squared is
H square is more small, no? It says you are limiting to 0. So h and h square, suppose I put h is 0.1, so h square will be 0.01. It's going to be small, higher order.
more compared to C2.
Yes. Now I multiplied with this a big C, maybe 100 or something. So that's why it become finite. And there is another choice, the case 3, which is also very this is also easy case when a is less than 4b. So you got a square minus 4b is imaginary, and where yes. So you can write it in the form that what is that whole m1? M1 can be written as half of minus a plus ik, some k, something k, and m2 is minus a minus I k, and the solutions will be x. Yes, is like same following the m1 plus hash, because even they are imaginary, they are not they are distinct root, there are no degeneracy, there are no repetition of the roots. So then you can just follow there. So only when you have the repetition you have to follow this one. Okay.
K is square root 4b นะครับ
Yes. So this is like this is k, and one I will come because this is a minus k. Okay, I go for another case. Is it okay? So now it is we are discussing the homogeneous equation. Now I make it a bit complicated. So suppose we have this equation. With a source term on the right hand side. So generally in physics we call it source term. If you go to force harmonic oscillator, this will be like e to the power I omega t or sin omega t. So it's like a driving force. It's a source term. And how do you solve it? So solving it, so this is also a linear, as you can see, linear one, because function of x not y, and there is no square or cube term. So this is a linear perfectly. And suppose I consider y1 to be a solution of the above equation. Okay, some solution y1. If I put y1, it should satisfy. That's my argument. And there could be another solution for this one. So I write the general solution is y1 plus y2. Okay. So if I put y to be y1 plus y2, this become but fx remains as fx because there is no y or y to substitute. Do you understand? This is a linear equation. First I say I know one solution y1 which substitute, and there is another solution y2, and then I substitute both. Since I know this y1 exactly why this one. So this kind of differential equation has two solutions. One is so what is another solution? What is the nature of the another solution? If you know y1 to be solution of this, there is another solution to make it complete general set is not d2 dx dy2 equal to 0, because I know this one is equal to fx, because that's my assumption at the beginning. So I put this one. So these solutions where I put a fx here, previously there fx was 0, has two parts. Okay, one is called the y1 is called y1 is called particular solution and y2 is called complementary solution. So if the complete solution for this is y1 plus y2, so that's the general solution for this one. So is it okay? The logic you understand? I have a equation, second order differential equation. Previously I studied without source. Now I have a source. Then I assume there is a solution y1 which satisfies this, and there is another solution which is also solution to that. I don't argue anything about that. Then I say the linear superposition of this has to be solution. Then I put it back. Then I there are two solutions. So even you know a solution which exactly satisfies this one, then it not the general solution for this system. You have to put you have to add the solution of the same equation without source, without fx term, then it becomes the general one. And I already discussed few minutes ago this one. You know how to do it. So now the question is how to do this one. This is not always easy that you can do this one, but there are couple of methods which you can do. I will just quickly review two of these methods. One is called D operators. You know D operators. D operator methods. So this is a technique for solving this type of equation. So what you do, you actually replace d by d dx. You write d dx is this, and so if you have dy by dx, you write simply dy. Okay, so this is called D operator. So for this D operator, the property of D operator is d2y by dx2 is going to be, you will write it d square y, and similarly dny by dx to the power n, you will write it dny. That's fine. Then the most interesting part is what is the inverse of d. So you got something like d square dn. Then the next question is what is d minus 1. So suppose I have du, d and d inverse of u, what is going to be d? Think about this one. this is the operator, yes. So if you, maybe I put D first, so this should be U, no? So this inverse is actually integration. So inverse is equivalent to integration. Integration. Now the question is, what is this then? Is this integration? Yes. So this is going to be you can take minus 1 by k out, and you can write it 1 minus d by k to the power minus 1. So this is minus 1 by k, and it becomes, you have to open the whole series. It should be 2 factorial k square, no? So if you have a function which is f of x, then you have to open it up and put the fx behind and do the operation. Suppose this is a x cube or x square, you will see after some iteration it becomes 0. So this is going to be truncated. Is it okay? What is the time? Yes. Okay. We have time. So let me give you a quick example for this. What is this? So what is the solution for this equation? Yeah. So then as the next step, what we will do, this is very simple. If you just to give you the idea how it works, but you can have many complicated examples of this. And so if you want to be master this technique, you can go to any textbook and practice it, but I give you the essential idea of this. So this is d square minus 8d plus 16 y e to the power minus 6x. Okay, so the y is going to be e to the power minus 6x by d square minus 8d plus 16. So what is this? What is this? I can write it 1 by d minus 4 square e to the power 6x. Do you agree? I just put d to the power 6x down. So now I can do the operation here. It's like the same. So it become am I doing something wrong? Let me see. This is minus 6x e to the power 6x. So what will be this? This will be so it goes inside, no? So this will be 6. So 1 by 6 minus 4 whole square into e to the power 6x as it is remain. Do you agree? Or even if you don't want to do it, you can do it from here. So it will be 6 square minus 48 plus 16. So this is going to be 1 by 4 into e to the power minus 6x. So this y, what is? But think this is the particular solution. Why? You solve the differential equation, but there is no arbitrary constant with this one. Yes, but you have not used any boundary condition also. So this is a particular solution.
So if you say again about why d becomes 6.
Why?
D.
Why db?
6 minus 4. 6 minus 4.
So it's a derivative of e to the power 6x. So 6 e to the power 6x. Yeah, okay, maybe we do it here. It's better. Yes, let's do it here. What we get. So d square minus, let me check if I did anything wrong. So e to the power 6x, no? Here. So the operator is this is 36 2 times. So 36 and 24 plus 16. How much is this? Is 24. Oh, there is a square. I might make a mistake. So 36 minus 24 is basically 12. 12 16 is 12 plus 16 is 28, no? So this should be 28. So why do I write this? I did some mistake, I think. Yes, because this was d minus 4. No, this is 48, no? Yes, that's why. So how much we get? So 36 and 36 is 42. 52. 52 minus 48 is actually 4. So you got the 4. Yes. Okay. Sorry for confusing you. So then it will be minus 6x. So now you see this is not a general solution because there is no arbitrary constant involved. So for the arbitrary, to find the general condition, you have to do with solve this equation without source. So that is d2y dx2 minus 8 dy by dx plus 16y equal to 0. Now you consider, as I tell, e to the power mx. So this is m square minus 8m plus 16 should be 0. So m is, you already know it, this is d minus 4. So m is plus minus, no, m is m minus 4. So m is 4. So but m is not only 4, m is 4. So then you have to consider that the general solution will be 1 by 4 e to the power minus 6x a plus b, yes, and you have e to the power 4x. So then e to the power 4x it goes, so it will be e to the power minus 2x. Yes. Anything, any mistake I did?
Is multiplied by
Oh, sorry. Yeah, I did. It's a plus. Yes. Not multiply because it's two solutions.
minus 6.
Minus 6. Yes. Sorry. So now I will try to move to the dynamical system part. So in case you want break, so you can go for break 5 to 7. So far you have learned how to find a solution for a given differential equation. That's okay. That's a great thing. Did I miss my class note? Okay. So now the question is that all? Finding a solution of a differential equation, is that so let me give you x. So here now I transfer my derivatives. Previously my all derivatives were dy by dx, but simply now I am doing it dx by dt is the same thing. Only the dependent variable for dynamical system is generally time, consider time. So if you solve this, what you get, dt is dx by sin x, and t is then cosec x dx, and the solution of this is minus ln cosec x. You write cosec, no, here? Yeah, okay. And cot x plus c. So you got a solution. Now I give you one initial condition that at t equal to 0, x is x0. So from there you can easily find that your c is ln x0 plus cot x0. Okay. So you can find the solution you are looking for, that is t equal to ln cosec so this is minus, so this goes as c, so this is cosec x0 plus cot x0 by cosec x plus cot x. Okay. So we got a exact solution for this differential equation, and then it's great. But now tell me, what can you tell about this, the solution? Can you give me what is the nature of the solution in a qualitative way? And if I ask you what is the nature when I write at t equal to 0 and x0 may be pi by 4, somewhere around pi by 4, and what will happen to the system when I let time to flow? Can you answer from that? You might have answer, but it's very complicated. You might get an answer for a particular case, but for this example is made difficult, so you can say for some cases it's very difficult to answer. So like I ask, if I put at t equal to 0 x equal to pi by 4, what will happen to the solution? It's not straightforward, you can see from here, but you have a solution for the system, and that's why then comes the use of dynamical system. It was actually developed by Poincaré. So when you study sun and Earth is rotating around sun, it's a two body system, you can perfectly solve, do anything, and if I just put moon, it's become a three body, it's complicated. You need dynamical system, and that's why to study those orbits, actually Poincaré developed this subject, one of the pioneer, then many people developed this one. So, but there is another pictorial way for investigating this one, more easier way to understand the qualitative behavior of this differential equation. So, if you consider t is time, and if you consider x is a position for this differential equation, and x dot is velocity, then you can draw a graph. And what is this? If I plot x dot versus x, so this is just a sine function, no? Nothing else. X dot versus x, it's sine. Okay, this is just sine. X dot versus x, so side like f of x versus x. So this is like velocity, and for here, for differential equation, there are some particular solutions which are very important for the dynamics. Is that when this x dot equal to 0, yes, x dot equal to 0 is these points. So that is 0, pi and 2 pi, yes, and this is minus pi minus 2 pi. You understand? This is just a sine wave. Now, if you consider these to be a vector, and the thing is, if x dot is positive, means the velocity is positive, draw a arrow towards right, and if it is negative, draw a arrow towards left. So then you will find, you will draw something like this, something like this. Yes. So suppose this is considered some value, positive value of sine x. So x dot will be positive, and this is some minus, sine minus theta is minus. Yes. But for here, when you cross minus pi, it becomes opposite. One minus will be imposed, so it will be positive again. So what do you, now I ask the same question, I release the particle at, this is pi by 2, I release the particle at pi by 4. So now if you consider this whole thing as something fluid, you have a fluid, one dimensional fluid, and this is like a sink and this is like a source. Sink, one source. So if I put a, so this is a source, water is getting out. So you consider a pipe. You have a water and some hole is ejecting, some hole is sinking the thing. So you can imagine a fluid or imagine a flow, and if I release the particle here, you can see the flow is going this way and it will be sink. So this will end up here. So you can just tell me from there what will happen, this solution will cross the pi by 2, then it will go and stop at pi, because pi is a x dot equal to 0, and it is a, we call it is a minima or stable point, where if you stop there. Yes. So is it okay? Is this make sense?
Yeah, I think you can you please write explicitly that the x dot is greater than 0, you just draw left or right.
Oh, okay. So x dot greater than 0, draw right arrow. Yes. X dot less than 0, draw left arrow. Yes. Yes. So this is one example that just solving a differential equation might not give you all the information you want to ask. So that's why the use of dynamical system. And I would like to show you couple of more, one or two more small examples of application of dynamical system, and we can try to see. And now let us consider even a simple setup for the dynamical system. So though the dynamical system is used mostly for nonlinear dynamics, but understanding the dynamical system of linear systems is very important, because when you go to the nonlinear system, you linearize it and use the method of linear system. But there are some exceptional cases where you could not use those things. So that's why I will be putting a great deal on the linear system, doing linear system, because if you know linear system, you know nonlinear automatically. So what will be the solution for this? Yes, this is the most simple linear system. Now depending on the, so you can check this is the only solution you have for this differential equation. It is easy to check, there is no other solution. This is and you can see one differential equation and one arbitrary constant. So so now you can try to see if a is greater than 0, what will happen? A is greater than 0, there could be k could be positive and negative. If k is greater than 0, then xt on the limit t tends to infinity is going to be infinity, because k is 0, greater than 0. And if for the same case k is less than 0, xt is going to be minus infinity when you take the limit t tends to infinity. If you try, so you are given a solution where you know the k is positive, a is positive, and then you know the qualitative behavior of the solution. When you allow the time to flow, the solution will become infinity. And if it is minus, then the solution will become minus infinity. Now the second case, if a is 0, so what is this? Xt is constant. Yes. So wherever you leave the particle, it will stay there, not move. Yes. So there is no dependency on time. And the third is, if a is less than 0, then if a is less than 0, whatever you got the k plus or minus, xt at t tends to infinity will go to 0. So yes.
y and then t approaching of yx.
No, not infinity. This is infinity. This is not alpha.
Is it
Infinity.
infinity?
Yes.
Okay, so that is also infinity.
Yeah. So this is like if it is plus, so this is plus infinity. Minus means minus.
So infinity should be number 8, right? But then
Okay.
no,
So
no, complete rotate.
complete this.
Yes,
Okay. Okay.
yes. For the benefit of mankind.
Yeah.
So that t approaching infinity, right?
Yes. This is also t is approaching.
Okay, please.
Okay.
Thank you.
Sorry. Okay. So if I want to draw the behavior of the solutions qualitatively, I could get this kind of informations. So what is this case? If I draw t tends to infinity, this is t, this is xt, and what is this case? This is a greater than 0 case. Yes? When you let the time flow, the solutions diverge. And you can have other system, other behavior of this where you write xt versus t. So this is a less than 0. So if you got so you know the solution, but this is a very pictorial way of visualizing this simple system. So for the simple system it is obvious, you can even see from the solutions, but it is good to know these techniques for more complicated systems so that you can understand the whole dynamics. Okay. Let me give you another example of dynamical system, which is we called this is called logistic population model. So dynamical system is often used in studying this complex system behaviors and behaviors of many like real life system. So one of the simplest is the studying the logistic population model. So suppose we want to describe the growth of a species or any species, and we took two different assumptions. So when population is small, growth rate is proportional to number of the species, number of the size of population. And the second part is population, the population becomes large growth rate become negative. So one can model this by x prime is ax minus 1 by x by n. So this n is the ideal number for the logistic you have. Okay. So like you have the supply of food, accommodation, everything, there is a maximum number which you can fit with the logistic supply you have. And if you see, if x is small, x prime is just ax. Yes, but when x prime go beyond n, more than n, so the growth rate will be negative, because that's a common sense. If you see from the logic, if you put more people in a place where there is less capacity, there will be fight, and eventually the number of people will low down because of many factors. So this is a kind of simple model.
It's like we have the Iceland and we put some the rabbit.
Yeah. It's actually like you can say like rabbit models also.
To the one
Yes. So yeah, that's true.
But then can you put comma after the small and large? Because otherwise I thought small is an adjective for growth rate. So that is confusing.
Small growth rate.
No, that's when population small and then stop. And
Okay.
Then, yeah, growth rate. And then the second also.
Okay.
Yeah,
And I understand. Yeah. So yeah. So you can solve this one. I can normalize this by making n equal to 1. So just I say that number of n, which is the maximum capacity for me, let it be 1, and then this system becomes ax 1 minus x, and you have to remember both a is also a positive number. It could not be negative. It could be negative, the rate could be negative, but a is a positive number. It could not be negative. So now once we do it, we can find a solution for this. This is a solvable differential equation. So dx by x minus 1 by x. Again. Oh, sorry. Equal to only a into dte. So what you can have this x t is k e to the power at plus 1 plus k e to the power at. So I leave it to you to solve it. It's a very easy solution, and at t equal to 0, if x is x0, then what you get, x0 is k by 1 plus k. So after putting this boundary condition, you will arrive at now, depending on the choice of your x0, you could have different class of different kind of solutions. Now what is most interesting here is, as you can see that there are two equilibrium points to this differential equation, which looks like x prime equal to a x minus 1 minus x. So x prime could be 0 in two cases, when x is 0 and x is 1. So there are two stopping points. Either there is no population or the population is equal to the maximum number of your logistic can hold. Yes, the one is the maximum number where you can accommodate with a system. So suppose I have a cage. I put some rabbits here, and I give some food, and my food supply is constant. Okay, so I give like W amount of food, and at the beginning there is only 2-3 rabbits. They will eat more, they will be happy, they will reproduce more. Then slowly I have a number which a rabbit can survive of the minimum food, and that goes to like number n. So even they reproduce, the number become more. When they cross this n, there will be shortage of food. So some of the rabbit will die out of the not having food. So number will go down. So this is the model. This is modeling this system. And even if it's for human also, it's true for the any kind of species. And if we do this, we could draw a graph for this. So this maybe let me draw it this way. Okay, so this is like I have so this is x equal to 1 line, okay, and this is x equal to 0 line. From here, what you could see that the solutions from here, if you put in between, they will go like this. They will go like this. And so if it is below 1, the growth rate is positive. The growth rate is positive, so it will go this way. And if it is negative, then the growth rate become negative, but this don't make sense for our model. This is negative population, which you cannot have. And suppose I have n number of rabbit here, which is equal to the, means I am in a perfect balance, and if you add more rabbits to the system, you will see they will fight, and you will settle down again to the maximum logistic limit you have. Okay, so this is very interesting way of studying some system like some complex system like this. And if you plot, how can I get this plot? So this plot, if you plot the f of x is this, or maybe x prime, I say x prime with respect to x, then you will get a curve like this. I am plotting this one, and for a chosen value of a. So if I choose some value of a, you will get this maximum will depend on the value of a you choose. And there will be this x equal to 0 point and x equal to 1 point, because you know from the graphical solution, finding solutions for using graphics, like you plot the function, and wherever they cut, these are the two solutions. These are the solutions. So it cut here and it cut here. So these are the two solutions in there. It is a solution for the system, but it's like two fixed points of the system. So between x0 to x1, you see the growth rate is positive. So that's what you see. 1 gets 0 positive. And if you plot this, this go negative. When you use more than x1, growth rate is negative. So you decay and can't.
Can you put the temporal axis on the picture?
Oh, this, yes, yes. This is time axis and this is x axis, xt axis. Yeah, sorry. Thank you for correcting me. So do you understand why dynamical system is useful? Even for a simple case where you have a exact solution of the system, but you might not get everything out of it. You need some more information. So I might make it a bit complicated by putting another a bit more complicated system to describe is this, that it has a constant harvesting, you know, harvesting, yes. So the model is very similar. Maybe I put this A to be unity also, it's not a problem, just for the, yes. So I have some H which represent my, yeah, H, which is like constant harvest, means I grow crops.
I think these 4 letters look the same for me.
Really?
Can you write it
Yes.
longer?
Longer H, okay.
It's like a call him in design.
Okay. So it's like I put some harvesting in the system, so there is, you are growing some crops and
I installed some font to you. Okay, now we have Tanya Roman.
yeah. So in this case I don't do all these things, but what interesting you can see from if you study this plot. So am I doing it correctly? I think so. So if you can get these kind of 2 plots, 3 plots which go like, oh, it should touch. So you can see this is, you have to find the fixed points, the roots, no? So this is x minus x square minus h equal to 0. So you can write x square plus minus x plus h equal to 0. Is it okay? Plus. So x is minus b, so 1 plus minus b square is 1 minus 4ab is 4h and by 2. So you can see the h has something with the 1 by 4. So if h is less than 1 by 4, you have 2 distinct roots for the system. So this line actually corresponds to h less than 1 by 4.
When you apply h x prime 0,
Yes, when I try to find a fixed point. So this is like x prime equal to 0. And this one, when h is 0, you got actually, no, h is 1 by 4, you got only 1 root. Yes, because this term is 0, so this is only 1 root. So this one corresponds to, and this is no root, because this one become imaginary. So there is no root, real root. So why I am showing this, if you model this system with h, this is very important to identify this point. This is called a catastrophe for the species. Let me explain a bit. So your harvesting is, if your harvesting go below certain, the production of food go below a threshold level, that will be a catastrophic case for your species. The species, number of species just go rapidly decrease. Okay. So if you draw the phase diagram, so this is the h-axis, and this is the number of fixed points you have. So like I write it x star. So this is h equal to 1 by 4, this is h equal to it's too much. H is, this region is, h is less than 1 by 4, and this is, h is greater than 1 by 4. Okay. So it is necessary that you identify this point. This is called bifurcation point, where you have two fixed points. There exist two fixed points, and this one is 1, corresponding to 1. The maximum limit is like yes. X star is the number of fixed points. I'm just saying.
Of fixed point.
Yes. And if you do the stability, you will see. So, so if you are studying modeling a social system or any complex system with dynamical system, this is kind of a very important point. This is called bifurcation point of your system. And the bifurcation point is the point where the fixed points are either destroyed or created. Means here you see two fixed points merge, and they become, there is no fixed point after that. So this is a catastrophic event, indicates a catastrophic event for your species if you cross this harvest limit. But if you, behind this one, you particularly have a stable configuration for the species. If your number go here and there, you can just come to and settle down to the balance n equal to 1 unit. But if you go beyond that, there is no stopping. So it's a catastrophic event. So this is another important point for why you study dynamical system. Is it okay? Any question? Oh, I have 25 minutes, I think. It's been, but I already start. It should be 10:40, 10:45. No, this is the, yeah, you can say this is the finish of this one, but I will now try to enter more mathematical things. So
does it have to be destroyed in pairs, or it can be destroyed only once? So
I think it can destroy one also, but there is like 3-4 types of bifurcation, like pitch of bifurcations, and what are the means, depending how you destroy or create, it has classifications. Like I think 3 or 4 types of bifurcations can exist.
So there is no forbidden.
No. I think there is no forbidden behavior as far I know. So it could be destroyed out of nowhere, and it could, yes. Okay. So I think is you understand until this point. I have another class in the afternoon, so I cannot finish now. So I have to do something more mathematical. I am going to try to show you. So till now we are dealing with one-dimensional system. Now let us try to make it a bit complicated. X dot equal to a x. So this is any linear system. Remember, I am dealing with the linear system. Till now I have not done anything to be non-linear. So it this one, but now my convention is going to change. So x is now xn, okay, and a is something a n cross n. So a is a n cross n matrix, and x dot is similar, x1 dot, x2 dot, the dot of these things. Okay. So what is the solution for this? In general, you can say a t and x0. Now remember, this is not only one x for me now. This is a column. Okay, so it's a higher dimension, not one dimension. It could be 2, 3. So for linear system, you can write these to be the solution. But again, remember, A is a n cross n matrix. So the hard part of here is finding exponential of a n cross n matrix and t. So this is, if you know this, then you know the solution. But it is not always that you know this. So if you have a diagonal n cross s matrix, if then you could do it easily. If it is a diagonal n cross n matrix, then it is easy to find e to the power at. But if it is not diagonal, you need to know the techniques to make it diagonal. Okay. So suppose I give you this one. Yes. So this is a linear system, linear and uncoupled. So there is no coupling between x1 and x2. So this is very simple. There is no x2 here, there is no x1 here. So this is a linear uncoupled system. So what is your A? A is actually -1, 0 and 0, 2. Okay. I can write this system as x1 dot, x2 dot equal to -1, 0, 0, 2 and x1, x2. Do you agree? Yes, this is very straightforward. Now you can find the solution for this. The solution for x1 t is c1 e to the power minus t x to t is c2 e to the power 2t. Yes. So, what if I write the solution in terms of the same kind of matrix, then you can write e to the power minus t 0 0 e to the power 2t and sum x0 x maybe x1 or maybe I put c1 and c2 some two constants. So, yeah, c1 and c2. So, now if I use this form e to the power at, yes, what is that? That e to the power has just entered inside for the diagonal case. If the matrix is diagonal, you can simply take the e to the power of all the diagonal elements. But this is not true when it is not diagonal. You need to make it diagonal, and that has many cases, sub cases of depending on your eigenvalues, the multiplicity of the eigenvalues, either it is real or complex, all those things are there. So, if A is diagonal, so e to the power a t is generally is a diagonal matrix of e to the power. So, diagonal matrix has the diagonal elements are the eigenvalues, no. So, e to the power diagonal element of okay, and this is a just special case when you got diagonal, and for diagonal we have this, and generally our aim is to find this one so that we can get the solution of the linear system. Now, let us look at these solutions, what we get, and try to draw the phase space of this solution, how this solution behave. So, you got x1 is c1 e to the power 2, x2 is c2 e to the power 2. So, you can express x1 in terms of x2, or there you can find the relation which is like x1 is going to be x2 is some constant, maybe k by x1 square. Yes, am I right? So, you make x1 square 1 by, yes, and where k is just k is c1 square and c2. I just club these two and remove the t from the system. Is it make sense to you? So, now you can try to draw the phase portrait for this simple system. So, what you notice, if this is my x1 t and this is my x2 t, now if I release a solution, suppose from here, release a particle from here. So, what will be the tendency of this particle? So, you see that the particle, yes, the particle has the tendency to, at t tends to 0, t tends to infinity. So,
The system is uncoupled, but there's a relation between the solution.
yes,
Because it's both independent terms.
yes. So, anything will be following this curve. So, at t tends to infinity, if you see that x1 t tends to 0, yes, t tends to infinity, and x2 t tends to infinity. So they have this tendency of the solution to for x to go to x1 to go to 0, again infinity. Yes. Okay. No, close is 8, no? Does it close? I don't know. Okay. It should close? Okay, like this? Okay. So if I release this one from here, it will try to decrease, try to go to 0, but on the other hand, it will try to go for x2 to be infinity. So this solution will go, so it approaches 0, this is the x1 0 line, and it goes to x2 infinity, and the same thing follow like this. You understand? So this is a simple example of drawing the solutions from the dynamical system analysis. And as you can see, there is only one fixed point for this system, that both of them are 0, and that is also unstable fixed point, means it's saddle, I think, it's not unstable.
Is there an easy way to define the exponential of A without like the general A?
No, it like you have to, if you have a general A, I think I want to discuss the general A. You have to, the most general theorem is this, what is that called? Jordan form. So you have to find the eigenvalues corresponding to each lambda, then you have to put the eigenvalues and make a P, and P inverse AP is going to be diagonal. Maybe this example, then I finish for the, this is a 3-dimensional example. So I just, so suppose I have the another simple system is x1 dot is x1, x2 dot is x2, x3 dot is minus x3, and you know the solutions for this one. X1 is c1 e to the power t, x2 is c2 e to the power t also, and x3 is c3 e to the power minus t. So if I draw this, how we will draw? This is a 3-dimensional case. So this is my x1 and this is my x2, and what you see that both of them are actually positive. So there is no going close. All solution will just run away from there. Do you understand? This case 1 was negative, so they had a tendency to go to 0, but here it's just fly to the infinity. And you have another axis in your hand, which is this one, this is x3, but x3 has a tendency to make x3 0. So what will happen with this solution? They will come like this and they touch this plane, go to infinity. They will come like this, they touch this plane and they go to infinity. Yes? x3, yes, x3. So if you can draw this diagram, what you know immediately, you can ask me any initial condition, I can give you the behavior of that solution. I don't have to check the differential equation and solve it explicitly. So this is the strength of the dynamical system. You can qualitatively study the system without finding a different solution of the differential equation. So if you have any question, or then I can continue in the next class. Yes.
Can you explain again how the evolution come from index graph?
This graph?
Yes, how the
This evolution?
yeah how the distribution y come from x1 and o2.
Okay, so you have to see these two equations, these two solutions. So I take t tends to infinity limit. So the x1 coordinate, anything with x1, something non-zero x1 coordinate has with time it will come to attracted towards x1 equal to 0. And anything will be with some x2 coordinate will be attracted toward the infinity. So if you take that count, and if you release a particle, suppose this is a flow of fluid. So if you release that particle, so that particle has a tendency to make it x1 0 but x to infinity. So you see this solution is going to x, this is the whole x1 equal to 0 line. So it's going close with asymptotically to this x will 0, but it is also making x2 to be infinity. So this is why, but if you explicitly draw this graph, they follow this relation. X2 is 1 by x.
We can choose any initial point, right?
Yes, yes.
If we want to look at.
Yeah. Any initial point and you follow that one, you know that. But you can draw explicitly using this relation between the x1 and x2. So let us start with the diagonalization. So as you have the examples I gave you before is all of them are already diagonalized by default that I gave supply you. So now the main thing is to find and to know about the diagonalization about any matrix. How can we diagonalize it? So what now I am going to do, it involve lots of theorem, lemma, many things, and we trust mathematicians, so they did it correctly. I am not going to prove anything. I have trust on mathematicians, so I will not prove any theorems.
You trust in mathematics.
Yes, so that's why I will not prove anything.
Are you sure it's mathematics? It won't be mathematics until it has been proved.
Yes. No, these things are already proved. So I trust them. I trust.
We are not both, so you can trust us.
Yes. So suppose you have a is a n cross n matrix and it is not diagonalized. So how do you diagonalize it? So the first one, the simplest scenario you can encounter, that if there is lambda 1, lambda 2 lambda 3 dot dot lambda n distinct real eigenvalue. So in this case you can construct a matrix P which is also n cross n by just putting the eigenvector as the column of this matrix. Okay. And this matrix will be invertible, so you can get a P inverse for this. And so this is your original matrix. If you do P inverse A P, you will get diagonal of lambda 1, lambda 2, lambda n. Do you understand? So this is the diagonalization technique, but I would like you to focus on this one.
So you have this n value of eigenvalue, right?
Yes, and you know the corresponding eigenvectors and make the column of this P with the vectors.
Did you talk about it before this?
No, no, because he described this.
Yeah, he just said something along the line.
Okay, but does he mention about how many types of diagonalization you can have?
No.
Okay, that's why.
He said, don't believe whatever you say.
Okay, so this is the most simplest one you can do, and then how do you solve a differential equation like this? This is, you have to choose like P inverse x, and then x is Py, and you have this equation. So you can put y dot is P inverse x dot. So what you get is P inverse A x. So P inverse A P into y. So if this is a B for you, so y dot is B y. So B is n cross n diagonal matrix. Yes? Because I have already diagonalized it. This is my B. It's the same thing probably Pradeep told. Right.
No, it hasn't come this far.
Okay.
It's eigenvalue.
Yes. So if you got this one, so you know how to solve this. This is diagonal. I say for the diagonal case, exponential you can just take inside. So you got yt is diagonal of e to the power lambda 1t, e to the power lambda 2t, e to the power lambda n t, and what you will have? You will have y0, and then you can do the inverse transform to x. So the inverse transform to x will be, so suppose this is your ET, the matrix is ET into y0, then the inverse the solution for the x will be P ET P inverse into x0. So this is one way you can get solution for a system whose the matrix is not diagonal. So let me give you an example, very simple example, what we do with this kind of things. Any questions over? Okay, straightforward. So let's take an example. So the example is x1 dot equal to minus x1 minus 3 x2 x2 dot equal to 2 x2. So now you construct your A matrix. A matrix is minus 1 minus 3 0 and 2. Do you agree? It is not a diagonal matrix. Okay. So then what you have to do, you have to find lambda 1 equal to minus 1 and lambda 2 equal to 2. Yes, please.
Okay, so it's just the same expression.
This one you're saying?
Yeah.
So I just like not, I don't want to write it.
Okay.
So I just put.
Different expression. So why not just behind?
Yeah.
Adjacent to the square bracket.
Yeah. Yes. So I believe you can do this. You have learned this in the previous class, that finding the eigenvectors for this V1 and V2. So the V1 and V2, the eigenvector becomes this. So now you know the lambda and you know the V. So you have to construct the P. Next you construct P. So the P is, as I tell you, take these two as column. So 1 0 1 1, and then you know how to find the inverse. No, I'm not going to do that. So you can find the inverse of this matrix, which is 1 1 0 1. So then you construct the B. What is B? B will be P inverse A P, which is going to be minus 1 0 0 and 2. Okay, so you got the B.
Do you have to have minus somewhere?
Did I make some mistake? Oh yes, maybe. This one is minus, sorry. Thank you. It's same, it could not be. I have to copy from note because I cannot compute this, it consume lots of time. It's simple, but it will consume time to find this inverse and thing. So you know, you see the B and it matches what I tell you before. It will be the diagonal of the eigenvalues. It will minus 1 and 2. Now you can solve for this B, and it is a linear system. So the B, if the B is like this, so your y dot become what is minus 1 0 minus 1 0 0 2 and y 0. Yes. So maybe I write it in a more y1 dot and y2 dot, and this is y1 0 y2 0 the init. So after doing this, you can find that y1 equal to c1 e to the power minus t, y2 equal to c2 e to the power 2t. And so you, as I say, you can get the xt from here. You need know the et. Okay. So let me write the solution for yt is c1 e to the power minus t 0 0 c2 e to the power, no, not c1 c2 e to the 2t, and I have here c1 and c2. This is the yt. Now this is, again you can see this is the et for me, so I can immediately compute the xt x1t. So this is very simple method matrix manipulation, so you can go and check if I am doing it correctly. I hope it is correct. And x to t is going to c to e to the power 2t. Okay. So, this is in your diagonal frame. So, diagonal frame, when you get something in diagonal frame, your system become uncoupled. Yes. So, this is uncoupled system. There is no coupling between y1 and yt, but once we do the inverse transform to x, so we solve the coupled system. So, what is the difference with this when we do it? What information you get is that you can solve some complex coupled system by this method, and if you draw the phase portrait for this, you have the y1, you have the y2, and so you see this is the y1, y2 frame. So, it is the same. y1 tries to go to 0, y2 tries to go to infinity. So, it looks like the same one I gave you the example before. Now, when you transfer back to the x coordinate by using x equal to py definition, so what you get is something like this. This is the same plot, but as you can see, the axis has been, it's not orthogonal. Yes. So, now this is x1 and this is x2. Yes. X is p into y, py. Okay. So, it's the p is the matrix you construct from the eigen vectors. So, next is I want to give you a kind of a table which I just try to make few hours ago, so that you can have a concise view of this diagonalization scheme. And otherwise, it's if I do it case by case, it's become very big. I cannot finish it. So just to give you, I like to have kind of 3 columns, and so here I have the nature of eigenvalues. Here is the P, how you construct the P, and here how can you get the solution. So, I already showed you one type. So, so you have the eigenvalues lambda 1, lambda 2 is goes to lambda n are distinct and real. So, if this is the case, you construct this P with V1, V2, Vn, and when you solve, you find this P into A, P inverse AP, and you have Y is P inverse X, and you know I just did the example what to do. Yes. So the next thing can come is the, suppose the eigenvalue was complex. So if the eigenvalues are complex, so let us consider A. So here A is the n matrix, n cross n. A is 2n cross n, because if it is all eigenvalues are complex, then it will always come up with pair. So always the dimension you can write as 2n and 2n. So if it is 2n cross 2n, so lambda j is a j plus I bj, and you will get lambda j bar a j minus I bj. Okay. This will be the form of the eigenvalues, because you will have the whole set of complex eigenvalues. Then you get eigenvector wj maybe some u j I vj wj bar uj minus I vj. Okay. So this will be the structure, and then how you form the P? The P you have to form this way. You put V1 U1, V2 U2, you know. So take one by one eigenvector, put U1 V1, and you will get the P. Now the difference is P inverse. When you do P inverse A P, this is going to be diagonal of AJ minus BJ and BJ and I think AJ. Yes. Understand? So this is for this case, this is the diagonal of lambda I. But here, if it is 2 dimension, this will be the case. If it is a suppose 4 dimension, so you will get block diagonal of this. If it is a 2n dimension, so you will get block by block. But this block coming is a block diagonal. Yes, others are 0. Only these blocks are blocks will be there. So and another thing is, if there is, so what I was telling you in the previous class, that how do you find the eigenvector when there is a multiplicity in eigenvalue. Do you know? So suppose you have A minus ki. The k is the eigenvector which is value which is getting not k, this would be lambda I to the power n into v, this should be 0. So for this case, if lambda is repeated n times for a root eigenvalue, they generally call multiplicity of something n. This is n, not x. Okay. So how do you find? So we know that if first you have to make it 1, then find the v. So you got the first one. Then you have to make that it square, then find the v. You got the second one. You do it until n. So you get the whole eigen vector space for this multiplicity of the eigen values. Is it Okay? You have question?
I can ask you later.
Yeah.
I don't understand why this work.
Yeah. So in general, like when we do eigen vector calculation, so we just follow the one n equal to 1 case. But when you have more, and this becomes the characteristics equation. You have to consider square, q to get the whole spectrum of the eigen vectors. So if this is the case, if lambda is eigenvalue of n cross n matrix, n cross n matrix A of multiplicity m. Multiplicity means how many times it got repeated. So lambda is, suppose this is lambda, it got repeated m times. So then you have to find a minus lambda I to the power m equal to 0. So find all the eigen vector. So here you could have mixed with the distinct root. So if you have distinct root, just follow the normal procedure, but the eigenvectors for the with the repetitive root, you have to follow this, and you have to find everything for that. And then as usual, you construct the P as V1, V2 dot Vn by using all of them, and then there will be this A. For this case, if there is a repetition, this A can be written as some S and N, sum of two matrix, and this P inverse S P is going to be diagonal of the lambda j and N, which is A minus S. How shall I write? Is nilpotent, I think. I'm not. Of order k, which kind of maybe less than equal to n. You understand? Okay, let me write everything, then I try to summarize. So for this case, your solution xt will be P diagonal e to the power lambda j t P inverse. So you know this is the kind of B, and there will be some part form 1 by n t plus dot 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 dot. S is some matrix. I give you an example so you will understand. So if there is a multiplicity like this and you construct this P, then actually you will have the A will be a composition of S plus N. N is a nilpotent matrix. Nilpotent means the matrix which get vanished after you after certain order, suppose this n is something, n square is 0. So this is nilpotent order 2. So means some higher order of that n is going to be 0. Do you understand? So it's like n to the power k is going to be 0, some k, and k is less than or equal to the dimension of the matrix. So I give an example, otherwise I know this will be like you feel lost. Let me give an example for each case. So the first case you already have the example, no? This one I already discussed it as the first one. So let us consider that this matrix. Sorry, k minus 1 means the kth order is 0 because it's do it, write it more.
Yeah.
So this term is actually n to the power k minus 1 t to the power k minus 1 by k minus 1 factorial. Is it okay now? Okay. Yes, this proof means is within e to the power lambda j is t. What I summarize in the table is it's one chapter completely with proof and lemma and many things which we cannot handle here with this. Okay, so I was talking about the example. So this is a 3 cross 3 matrix, and you find the eigenvalue. Yes.
So do you mean the square matrix just multiply it by?
Yeah, this one is multiplied by this one. It's continue. I should have made the table form here. Yes. So lambda. So if you consider this, there will be lambda 1 is 3, lambda 2 is 2 plus I, and there will be lambda 2 bar, which is 2 minus I. Yes, you go and check, you can find this, and 1 0 0 and W2, which is U2 plus I V2, this will be 0 1 plus I and 1. Yes. Yes. Yeah. So if you have this, so now your duty is to construct the P 1 0 0. So I put like this 1 0 0 0 1 1 0 1 1 0 1 0, because there is no 0 1 0. Is it okay? So this is like you have to break it U plus IV style. And you can just do some manipulations and follow the standard procedure, and you will arrive at the inverse of this one.
So your P, the last one is not 0, right?
No, this one?
Yeah.
Because you have the I.
Yeah, but you have 0 there. Seriously?
0 1 0. Oh, 0. Oh, this one, no?
Okay.
Yes, yeah. This is 0 1.
Otherwise your P is not invertible.
Yeah. 0 1 1. That's good. Because yeah, this is 1. Yeah, that's good. And then you have to find the same B. B is P inverse A P, and P inverse A P is minus 3 0 0 and 0 2 minus 1 0, 1, 2, I think. You see this form A minus B, B, A. Where is A? A minus B, B, A is 2, B is 1. So if you have higher order, the corresponding to this, there will be blocks going for this case. Now, how to find this exponential of this, because this is your B, and now you know y is e to the power b into t. Yes. So, the thing is that if it is a block diagonal, then you can have the exponential inside, and proofs are complicated, but just hold on there. I give you some formulas and probably one proof I try to give you.
So this is only work for the real value matrix, right?
Real value matrix.
Because
Yes,
if
that's.
you in the complex field.
Yeah, complex, no.
Okay.
The assumptions, if I write theory, the theorem exactly, they say n cross n real valued matrix.
Okay.
So, but I am not going to write it. What is that? Sorry. So, there will be for this, as he said, this real valued matrix. So, if you diagonalize this matrix, there is a theorem form called Jordan form, which says you will always encounter some blocks, even how many bigger dimension of the blocks you go, and these blocks has 3 forms. And you know you can compute the exponential of that 3 block form, which is very easy. So, the case 1 is, just hold on there, I then discuss about that one. So if you have A is A minus B, B and A, so if you do e to the power A, so for any arbitrary case, e to the power A will be summation over I A to the power I by, no, it is summation over A to the power I factorial I, no?
Yeah.
And there will be I goes from, this is the general form. You can do it for general form, but you can do it some for some easy way. So you will get e to the power A cos B minus sin B and sin B and cos B. So if the matrix is in this form, you can compute the exponential of it, and the proof is very simple. So that's why I only want to give it only one proof. it will take less time, that's why. So suppose you have the matrix A, which is A minus B, B A and whole to the power K. So if you apply the method of induction, means you do it many times, then you will see the pattern is this: real of lambda to the power K minus imaginary of lambda to the power K and imaginary of lambda to the power K and real of lambda to the power K. Okay. So the idea is you take it, multiply 2, 3, do it, and you will say you will arrive this induction by method of induction. You know, by method of induction, you know, no? So you identify the pattern after doing certain time. You do it in legendary or Harvard polynomial when you try to solve. And then if I try to put e to the power a is going to be, suppose I have k summation over 0 and careful infinity, and so because factorial k will be a constant, no, for e to the power a k, so you can absorb it everything, and lambda to the power k by factorial k, and imaginary lambda to the power k by factorial k, and real lambda to the power k by factorial k. Yes. So this is e to the power lambda, e to the power lambda, e to the power lambda, e to the power lambda. Do the sum each by each, add one by one term. So this will be e to the power lambda, e to the power lambda. So then once you do it, shall I rub this part? Is everyone done with this one? This part? Okay. Okay. So then when you have there is real of e to the power lambda, imaginary of e to the power lambda, and then again imaginary of e to the power lambda. So you will see, you can expand it, e to the power lambda, lambda is a plus ib, a go out, and this you got cos b minus sin b and sin b cos b. So if a is 0, is simply rotation, a rotation matrix, yes, rotation by angle b. So now you believe me, there is proof behind everything I am giving. Okay. So this is the simplest one I wanted to give you, and the similar form, the case 1. So this is case 1. Now case 2. Case 2 is if a is this form, a, b, 0 and a, then this is also have proof. This proof is also small, but I will not have time to do it. 1, b, 0 and 1. And case 3 is, you already know, a is mu 0 0 lambda, just diagonally to the power a e to the power lambda 0 0 e to the power mu. Yes, you know this is the diagonal you go, and this one also have proof. I don't have time for this one, is but can be proved. So now come back to this one. You see this one, no? This form. So which one? This part, can I erase? Okay. So if you go and check, you can have this e to the power minus 3t, because this is 3 and this is 0 0 and 0 e to the power 2t into cos t minus e to the power 2t sin t, and e to the power 2t sin t, and e to the power 2t cos t. So you got this P inverse into y0. Now you have to come back to the x again. Yeah, this is x. So to get the final answer, you have to multiply this one with P inverse, this one, and then with P.
So is it mu or something?
Which one? Mu. Yeah, mu and lambda.
But mu is what?
These are two distinct eigenvalues.
Or you just name
Name
it.
it, yes. Means I give three cases. The idea is very simple. For the diagonalization, if it is a real matrix, you will encounter the block even for any arbitrary n cross n dimension. The blocks will have these three different blocks, and you know they are exponential. So you know everything for this system. Yeah, this there will be a z. Yes. So now you can try to see. This is exponential 2t, so this plane and this will divert. Yes. So x2 and x3 plane has the positive of exponential t. The coefficient of exponential is positive. So the solution should run away to infinity, and this has it try to come to the x1 equal to 0. So if you draw the phase diagram for this, you can use some computer to generate it, but just I give you this how it will look. So but now you see you have cos and sine, that means it will be having some rotation. Sine and cos is associated with rotation. So some solutions will go like this on this plane, x and x2 plane. Then you have the third axis, which is x1. X1 axis will so it go and mix to the plane. Understand? Because okay, what is the time? How far? I have started. I have half an hour. Okay. No, I started at 3 around 20. No, but I need half an hour. So, then I am not going to discuss the multiple case because I will not have time for that. Like with the eigenvalues with multiplicative factors, like so yes, but I give you the example. I write the example and you can try at home, and the method is same. So if you have this A is 1 0 0 minus 1 2 0 1 1 2. So if you have this, you will have lambda equal to lambda 1 equal to 1, lambda 2 equal to 2 and 2. So the A minus lambda I to the power n equal to 0. So first you consider this to be there will be b 1, so you get the b, and then you consider this to be 2, this is also 2, so then you got the v1 and v2. Now it perform this, but you have to consider the method is different. There will be a nilpotent matrix. I am not sure if I should do it. I will not have time to finish it, or maybe I just give a quick, very quick I will be writing. Okay, believe me, I can make mistake. Okay, you will get v1, v2, and the v3. As I told you, v3 you will get something 0 1 0 something like this. Then construct the p 1 1 minus 2 0 0 1 0 1 0, and similarly there will be a p inverse which you can compute. Yes. So you remember? Yes.
What do you mean by 2, 2?
Uh,
To have two values, but in the same.
yeah, two same values.
Two again values.
Yeah, two same eigenvalues.
So lambda 1 is only one, right?
Yeah, this is 1 and this is called like degeneracy of the eigenvalues. And for this case, the procedure is a bit different. So then, as I say, you can have a S, you can construct a S matrix. So I was saying you that P inverse SP, I think, is P inverse SP is diagonal of lambda, you know. Yes, let me check. Yes. So now, if you know the lambda I, so you can find the S. S will be P diagonal lambda I into P inverse. Yes. You know the S. You know the P.
Yes.
You know the lambda I. Make the diagonal matrix here. Do this computation. So then, then you can have n. N will be A minus S, and this one I write. This one will be 0 0 0 0 0 0 minus 1 1 0, and if you check, n square will be 0. Then the solution will be xt will be P and P inverse lambda, this diagonal of lambda I into inverse
e to the power lambda I t.
yeah, e to the power lambda, sorry, e to the power lambda I t, and then 1 plus n t into x0. So this will be the solution, but this is not the final answer. You have to compute everything. You remember there was a series for this. So because this will be always a nilpotent matrix, equal to or lower than the order of the matrix, so this will be always truncated at some point. So we will get the answer for this. So far so good. Any question? That's why I telling you no, I will not try to enter. But I am dealing with the linear system only. There is no non-linearity till now.
Basic camp.
Yes? Yes. Everyone dead. So what if you allow me, so what I try to give you, you can just keep it in mind, and I am following this book by Parco, Lawrence Parco, I think. This is a famous differential equation and dynamical. So you can go Parco.
You have the PDF.
Yes. I have the PDF, and this book is a bit mathematical, but you can try to follow. So now, so what I try to convey you that there is always for real encroaching matrix linear system, there is always method to diagonalize it, and the most generalized one is the Jordan form, where when you diagonalize, these three blocks will come blocks, and you put the e to the power, you solve any n cross n matrix, any coupled equation. So you can see the power of this method. Any dimension you can solve here, the coupled. You understand? Linear. Don't touch anything non-linear. You have some question? So let us Now do something very quick about two-dimensional system. I have not entered planar. So I told you these are the two forms.
If you teach more, I will teach more, and then they not get to eat.
They will not eat. Okay, then just let me continue.
No, sorry, just joking. No.
Because I have not got my allotted time till now. I'm running. I should have time. Allotted 10 minutes because I have not finished. Got my. So if you have B, which is lambda 0 and 0 mu, just give me 10 minutes to conclude it. Or B, I told you that you can diagonalize anything to this block form. So suppose you are in a two-dimensional case. So you can draw the phase portrait for this. So first let us draw for this B equal to maybe B1, B2, B3. Let me try with the B2, this one. As I already showed you. And what is the case for this? That lambda is less than 0 and mu. So if the eigenvalue 1 is negative, 1 is positive, you got a saddle point at the middle. And if you have the, what is the case? Both of them are negative, so you will get a source. So not source, sink. So mu, lambda, both are negative. Okay, and now depending on which one is bigger and which one is smaller, this phase portrait can be not straight line. Sometimes you can go something like this, depending on the value of the lambda and mu ratios. So this is also the case, and so you can get different type of phase plot in two dimension. And this is A minus B, B and A. So this is, I told, yeah.
The third case is what?
The third case is, it is the case for when lambda is less than mu. Both are negative, but it is more less like. Then this phase it got distorted. It's not like a pure sink. It got some distortion depending on the.
So the top is when mu is less than.
Yeah, and they are, I think, equal also, equal and less. So you got like everything is going directly. And when this matrix is in this form, yes, it's going to rotate. Oh, no, okay. Two are same.
It can be all over an hour.
Yes. So if your A is negative, so because if you remember the A come e to the power A cos B minus sin B cos B. So this is kind of amplitude. So if A is positive, there will be a T here. So the amplitude of this will be a spiral. It will decrease and go to 0. And depending on the B sign of B, if B is greater than 0, you will get this is anticlockwise spiral. Yes.
So this one is for B2 or for B1?
This is for B2, and I am now discussing B3.
But then why not B1? Because we also have B1.
B1 is this one. It will be the same.
That's it.
Yeah, I should. I'm just rushing.
All right. Okay.
No, yeah, both are B1, I think. Both are B1, and this is same like lambda, I think.
Then that's one left. That's one. It's not diagonal.
It's not diagonal, but if you get the
One on top right.
yes, this is like if you have the solution for this e to the power lambda t minus e to the power t.
I mean, this is not diagonal, so even mu is equal to lambda.
Yes.
So it's not the same. B1 and B2 are different.
Mm,
It should be 0. 1 should be 0.
no, because this is the 3 block cases I mentioned, which you will have.
B1 is for that, and B2.
Yes, and this is for both mu and lambda is 1. I have to check. I might mix something here. Yes. Oh, this is the case 1. This is the case 2 actually. B1 and this is B2. Right. This case is B2. Let me check the book. I have mixed something. Actually, when lambda equal to 0, these two have the same form of the phase plot. Not 0. Lambda is less than 0. So,
The same form.
yes.
But then but you have 1 over there. So,
Oh, okay. Let me draw for this one. The case is like this. For this one, it will look like this.
I used to draw this ages ago. I totally forgot.
Yes, this is the B2 case. I forgot. Sorry. So, actually, you see there is a fight. If it is in minus, there will be a fighting between this term and this term.
Oh, so that one is B2 and this?
This is B2 and this should be B3 and this is actually B1 also. This is the sub cases of B1. So I can do like this. This is B2 and this is B3. Yes.
I think it should be B2 because it's a tractor.
This one?
Yeah, this tree is a tractor. That is the repeller.
This one?
Yeah. This 1, 2, 3 should be the same dynamics.
Yes, they are same dynamics, but the phase portrait is different.
Oh, so
This is like a sink,
Yeah.
straightforward. This is like means if it is a sink, so you know this solution, the curve is x equal to alpha y or y equal to alpha x.
so this 1, 2, 3 is B1?
This 1, 2, 3 is B1 because of different choices of lambda. So this one is when lambda is less than 0, one is positive, another negative. So this is saddle, and this is saying that even both of them are negative, but you could have some different kind of dynamics. But it is a stable point. That agreeable.
And all of that is B2, right?
Yeah, all of that is B2,
Yeah.
and this is B3.
And which one is A negative and which one is B positive?
This one is A negative.
In the Schumann.
For all case, for both these case, A is negative. So that means this will be AT if you remember, and A is negative means this is the amplitude part. So this decaying with time, and the spiral, which way you spiral, it depends on the choice of B, and you can think from here like B is increasing or decreasing. It's a theta part. So this is B positive means B greater than theta increasing and decreasing. Yeah, this is B is negative and this will go this way. Okay, so now I just take 2 minutes to conclude it. I think I don't have, I will not, but there is another special case. Let me B, which is 0 minus B, and for this case A is 0 and B is 0. So this will gives you again circular orbits on space. Again, depending on B, we will have B greater than 0, B less than 0. Depending on B, you will have the circulation direction. So this is what I wanted to discuss to you about linear system and stability. But what about nonlinear system? I have not touched it. So I just say one theorem, what is called Hartmann and Gromman, two guys, they are men. Yeah, theorem which says if a fixed point, that I don't have time, if a fixed point is hyperbolic, means hyperbolic, locally the dynamics is equivalent to linear system. So if you have a, so this is my statement, but if you go mathematician statement, this is a homomorphism and many things will come. It's near about the neighborhood of this fixed point, there is a homomorph relation between this and that. So the idea is this: you have x dot equal to f of x, a nonlinear system. Maybe I do it here. You have x dot equal to f of x. This is a nonlinear system. So, and what the next step is, you find f x0, the value of x0 for which you got this to be 0, the fixed point to be 0. Then what do? You find the Jacobian matrix, and which is equivalent to del x at this x0, and find the, so this will be a matrix like, suppose you have del f1, del x1, and like you go like del f n x by del xn, something like this, and like this will be f1, then f2, f3, and then you got the del f n x by del x1 and del f n x by del xn. So try to find the eigenvalues. If at the fixed point x0 all eigenvalues are non-zero, so there is no zero eigenvalue. You can have your complex. So the Hartmann-Gortman theorem, like use the linearized system to find the stability of that fixed point. So this is the same, because now you can go for any nonlinear system and check, linearize it. Like you have to find the Jacobian matrix, put the x0, find the lambda. If there is a no zero value in lambda, whatever I taught you for the linear system, just apply it. But if there is a pure zero value, it's complicated. So now I leave it to you.